Okay. Final exam review. Exciting. I also just want to say um, I am looking forward to reviewing and grading your final projects. It's been a lot of fun watching them get built over the last few weeks. So, yeah, that's going to be really cool. And I know you guys have all been building some really, really exciting, fun stuff, which is awesome. So, for the final exam review, I have created a Frankenstein slide deck from pre-existing slide decks. I think a lot of this information will be helpful to review. I think some of it is going to be maybe less helpful because it's very, very fresh and recent. In particular, I think the Swift UI section is going to be helpful and maybe reviewing async await as well, concurrency. But before I get to that, I do want to make this like the first section here is for questions that people might have about particular topics. And then we can go through the deck if there's time afterwards. But do anyone have like questions where, I'll pull up Bex code or I'll draw on the whiteboard or anything that, upon beginning the review or the studying where you were like, oh, this didn't make sense that we haven't already, covered. Cool. Okay, great. I'm an amazing teacher then. You all understand everything all the time. That's great news. Cool. Okay. So let's hit this deck then, and then we'll hit questions as we go. Please feel free to interrupt me, raise your hand, or just talk. That's how my family is when I was growing up. We all just talked over each other all the time. I'm used to it. So if you just start talking, I will usually stop and listen. Okay, right. So let's get started. We're going to basically run through the entire class at lightning speed. I have breaks baked in. Depending on the timing and how quickly I go, we may or may not actually do those breaks. All right, so to start with, we're going to talk about core Swift. First, functions. Okay, what is a function in theory? It's a reusable block of code, a black box that gets inputs and provides back outputs. It accepts parameters as its inputs and it provides a return as the output. It can be called within the scope it is defined in, much like a variable can. You all should know this very strongly because you use functions all the time. In practice, they are actually blocks of code to execute. The definition includes your identifier or name, the parameters, the return type. The definition is the unique ID for the compiler, not the identifier. The definition as a whole is the identifier. And the definition as a whole can also be used as a type, which we will see shortly. All right, when do we create functions? When you have code you don't want to write a second time, code that you want to vary based on input, code to change something or calculate something. This is how you define and call a function. This is what it looks like. You all should know this. You've been doing it all the time, especially in your final project. Calling the function, once again, you call it using the argument labels as they are defined in the function definition. Here, we're currently using the same labels as the parameter names are because no labels have been defined. You also have your return type and the assignment type. What is returned from the function is what you can assign using that value. That's what the expression returns, calling the function. You call it with the identifier. That's how you say, hey, this is the function I want to use. Interestingly enough, because the name is not the unique ID to the compiler, you can have functions with the same name as long as they have a different parameter list. That's okay. It's called function overloading. We didn't really cover it, but it's interesting. And then here we've got our argument labels, parameter names. Cool. So many animations. I just copy pasted these slides, so not all of them. I did edit some out, but some of the animations came through. Apologies. Okay, so this is the argument label breakdown. You'll remember this. You get a default when you just do a parameter name. If you specify an argument label, then that's the one that has to be used when you call the function. And then you can do something called omitting an argument label, where you give an underscore instead. And in that case, you do not need to provide any argument label. In fact, you are required to not provide any argument label for that particular parameter. So there's 3 things you can do with argument labels: default, provide one, or omit one. And here we're omitting it. Oh, default parameters. If you assign a value to the parameter inside the definition, then you get a default, which means that is an optional parameter. It doesn't have to be passed in. Okay. So here we look at the print function as it is defined in Swift's API. It has multiple parameters, default parameters, and omitted argument labels, so it's a great example. It also has a new type called any ... something we hadn't seen before at that point. This is a variadic parameter, which means that it accepts any number of parameters of that type and then treats them as an array. Click. There we go. Another example of a variadic parameter is here. You can pass in 0, 2, 3, 4, and numbers. The parameter is treated like an array of ints. Okay, function types. Function definitions as type. Function definitions are considered a type in Swift. They are a type, they are a reference type, like classes and actors are. They are not value types, which means when you pass a function type, if you pass a function around, for example, then it is that same instance of the function that gets called when you call it from multiple places, okay? It can be stored in a variable or a constant. That variable or constant can be used to call that function. Storing a function, this is a function as defined. You can do storage just like this. You don't actually have to use closures. This doesn't usually get done. Primarily, people use function types with closures, not this way, but this is something you will occasionally see, especially if you have another function or class method that takes in a function type as one of its parameters. You pass in, let's say you have your own function, your own method on your own class, and you just want to pass that in. You don't want to make it a closure. You don't want to wrap it, anything like that. You can just do it like this. And this is what the type looks like inside. At the time, we didn't really care about sendable, and I think I have a little cross out on it, yeah. But we do remember now that at this point in time, we now know that concurrency in Swift 6 requires that if something can be sent across concurrency domains between 2 different actor executors, then we need to mark it as sendable. And so that's what this is saying, is that this function type is sendable. And this is what a function type looks like. This is how you define them. You have your parameter type definition. Come on, clicky, clicky. And your return type definition. And then you also have a function type. That's the whole thing. The whole thing is the function type. So you have 2 pieces to it, and that's how you define one. Parameter type, even if you only have one parameter type, you do need to wrap it in parentheses. The return type, you do not wrap in parentheses. That's how you write function types. Cool. So when can you use them? You can use them as variables. You can use them as parameters. And you can use them as returns. Basically everywhere that you can use other types. Closures. Closures are a specific type of anonymous function that you can assign to variables and whatnot. Anonymous functions are functions that are defined inline. They are scoped to whatever scope they're in unless they escape it, right? And yeah, so they're just slightly different from functions, but not really. They're basically kind of the same as regular functions. They're just defined differently, okay? So here we have a function. This function prints first reminder, and it takes in, the function doesn't print first. We print first reminder. The function takes in a reminder closure. The reminder closure is a function type that takes in 0 parameters and returns a string. Because we have that as the last parameter in our parameter list for the send reminder function. That means that we can define the closure in line immediately after we call the function send reminder without even using parentheses, right? Very common pattern in Swift. You'll see it all the time. You see it all the time specifically in Swift UI. We do it a lot in Swift UI. All of the modifiers where you have a block afterwards, that's how they do it. They're doing this, okay? So that's this. Right, and then it prints first reminder, closure reminder, last reminder, which you could probably guess. So this is a quick review of closures. Then we have escaping closures here. So escaping closures are closures that continue to stick around after they've been passed into a function. Swift can detect when this happens, and it will give you a compiler error if you try to have a closure that escapes without marking it as escaping. So in this case, the closure that's passed into save reminder escapes because it is being appended to a list. So it is being preserved via external reference. Some external outside of the function variable or constant is given a reference to the closure. And because function types are reference types, that means it gets preserved and continues to exist in memory. Okay? Therefore, it escapes. It is no longer constrained to just the save reminder function. It's not guaranteed to run or execute within there. It can also be preserved by other escaping closures. So if you call a closure inside of a escaping closure, then or pass it to an escaping closure, then you end up needing to mark that closure as escaping as well. And they kind of chain virally, which is relevant for when you're looking at things like dispatch queue. Luckily, we don't have to worry about that too much anymore because we have async await now, which is cool. And we'll look at that in a bit. But first, we're going to take a quick look at enums. So here's your basic enum definition. You have enum, name, case, etc. And then you can have an array or a set of enums set in this way. You can also have, for very long enums, you can use these commas, although this particular format is not preferred if you were to use like a common Swift linter. Swift recommends typically, you either have everything in the new line or everything in one line, and doing a mixture like this is discouraged. You can also nest enums inside of each other, have enums inside of enums, and you can continue this kind of ad nauseum forever. This is true for types as well. You can have enums inside of classes or structs inside of enums or whatever. It's a form of namespacing. It just kind of creates it just kind of appends the types together to make a particularly long type that you can then reference easily within the exterior type, and you can also reference from outside the exterior type. Enums with associated values. You can pass values in with specific cases of enums when you assign them. When you define an enum case, you can select to have an associated type. Whew, words. And when you do that, that means if you ever need to assign something to be that case, you are required to pass in the associated type for it, which means that you can store and continue and propagate data. This is typically done using errors, especially for networking. You can pass along networking HTTP codes and other errors inside of enum cases, which works well because error handling is done via the error protocol, which is implemented primarily by enums. And here's a slightly more complicated one. Not terribly important. You can use enums in switch statements. That's primarily how they get used. You switch on the enum, you go to case of the different enum types, and then you can do what you want to do within there. And that's how you use enums. Structs. With structs, they're value types. They're defined in almost exactly the same way as classes, which we haven't looked at, but we will. Structs have properties. Properties are pieces of data that you store within the struct, and then you have to assign them when you initialize the struct. This is the default initializer, which gets synthesized for you when you use a struct, which is very nice. Structs can also have functions within them, also known as methods. that can run functionality on that specific instance of the struct, or in this case, copy of the struct, because structs are value types. So they just copy around. They don't have instances exactly. Not technically true. Swift does something called copy when needed. So it's actually a reference type until it gets written to, but that's a fiddly detail that you all don't need to know. It never comes up, or it should never come up, if Apple's doing what they're claiming they do correctly, which they almost always are, but sometimes they mess up. Cool. Okay, so this is how you do functions within structs. Then you call it like so, and it remembers the information because it's stored there in memory with the struct, and it'll print out the magnitude because it ran the function correctly. Cool. Okay. You can also have computed properties, which are a special form of function that wraps around a property. This kind of does a bunch of stuff inside, but basically it kind of creates a private magnitude variable and then creates special functions around that private magnitude variable that get used whenever you call, a vector3 dot magnitude. My goodness. You can also have lazy stored properties. Lazy stored properties aren't set until they get called. That's pretty much what the lazy keyword does, almost always. You can also define your own custom initializer with structs instead of using the one that was synthesized by Swift. That's helpful if you ever have work that you need to do inside of the initializer, or if the way that information gets passed into your struct is not necessarily in the same format that you're storing information in the struct. Structs can also have functions that mutate them. Typically, structs are immutable by default. However, you can use the mutating keyword in order to make it so that a struct can be mutated internally. And then there's also the concept of statics. You can have static properties or static functions. Statics are essentially global pieces of state or functionality that you access through the namespace of the type. So, yeah. Classes. Classes are just like structs, except they are reference types, which means that if you have one instance of a class and you pass it somewhere else, you change it there, you don't return anything or do anything else. When you come back to your original code, the stored properties and stored information in that type instance are now also changed. You have to define your own initializer for classes. You don't get one synthesized for you like you do with structs, which is unfortunate, but it is what it is. And yeah, that's sort of the main difference between structs and classes. Yeah, reference type. Protocols. So protocols are how we do interfaces in Swift. Apple doesn't call them interfaces because they like to be special and fun and weird. They're basically interfaces with some slight distinctions and differences in how they do dynamic linking and all that stuff. And it's, whatever. It's, for our purposes, we can consider them to be interfaces, which is how you do multiple inheritance. So with a protocol, you can define requirements that structs or classes or actors or enums all have to conform to. So they adopt the protocol by declaring struct blog post :content, that's adopting the protocol, and then by actually doing the things that the protocol requires, thus allowing your code to compile, you quote unquote adopt the protocol, also known as implementing the interface in every other language. You can also have protocols can inherit from each other. So here content is inheriting from identifiable, which means that this actually will not compile because identifiable requires that we have a stored property named ID inside of it somewhere. Or sorry, not stored, it could be computed, I think. We just need to have an ID property inside of our type that conform in order to conform to the identifiable protocol. Excuse me. So you can also provide default implementations for any type that implements your protocol for function requirements. So protocols can require functions for conformance, and that in that case, if you have some base functionality that you want all users of your protocol to be able to use, right, without that you don't want them to have to implement their own version if they don't want to, you can provide a default implementation. Of note, there's nothing you can do to stop them from overriding the default implementation. That is something that only, like there's no way to prevent it, right? The class conforming to you gets to decide how it conforms to you as long as it follows all the rules. So if it overrides your default implementation, it overrides the default implementation. But if it doesn't, then the default implementation is what gets called when that instance or copy of the type is being used as if it were the protocol. Cool, that was protocols. Generics. So with generics, you can define a special generic parameter type that is a type of unknown definition. All you're saying about it at the time is that we don't know what this type is, okay? This type could be a string, it could be an int, it could be a glibglorb, right? We don't know. It's determined by whoever calls the function, right? In this case, where we are using generic functions. So this zip function here is a terribly complicated way to get this concept across because we also do this type alias key equals element thing. Basically, the array class has a generic type called element, right? So when you're dealing with an array, when you first define it, you have to pick a type, right? Either using the generic carets or by just assigning values to the array using an array literal, right? Or by using the, put the type that you want to be the element and then put brackets around it. There's a few ways to do it. But whatever you pick, that's what is set for the element type. So that type of unknown is set to element for each instance of an array or copy of an array, okay? And so the function here, zip, we have a value generic type parameter, which can be anything. And we pass in an array of those values, right? And then we return a dictionary where the current type of the array that we are extending is used as the key for the dictionary, and then whatever the value was of the type of the whatever the type of the array of values that was passed in is used as the values of the dictionary. So you can, for example, combine an int and a string array and zip them up together such that the ints all point to individual strings. Okay. You can also have generic types, much like you can with generic functions. As we were saying, the array type is a generic type. You essentially define your generic type parameter for a given type, and you say, hey, every single stack that we have, we require that we know when we create the stack what the element type is. It's a type of unknown origin. We don't know what it is or where it's coming from, but we need to know what it is for each instance that gets made. You can also perform constraints on generics. Inheritance constraints, yeah. So you can do inheritance constraints on generics, such as t:\content here on the publish function. That says that the publish function is available when, and only when, t is a type that conforms to the content protocol, okay? So only if the type t is a content protocol type, then we can call publish. So if you try to call publish and pass in something that is not conforming to the content protocol, you'll get a compiler error. All right. You also can have something that looks a lot like generics in protocols. using associated types. This is similar to, but not exactly the same as associated values in enums. They have similar names, but they're not exactly the same. So basically, in order to define a generic for a protocol, you use associated type. So here, this content protocol has an associated type of content type. So content type is your generic type parameter. It is a type of unknown origin, okay? Which means it's not clear what that type is. So any type that conforms to the content protocol needs to, by its own definition, make it very clear what the content type is, okay? So if you were to adopt the content protocol and conform to it with some struct or something, you would need to, when you define the property var content, you can't use content type in that struct. You need to pick something, and that is the content type, and it needs to match with the content type that you use in the mutating function update with new content definition, okay? Otherwise, you'll get a compiler error. All right, that was associated types and generics. Now on to concurrency. I think we're close to done with core Swift stuff. And then we will start to look at Swift libraries after a quick break. All right, so concurrency. I think I only have the one slide here. That's okay. So here we have an actor that uses async await. There's a lot going on here, so we're going to take some time on this slide. So if we'll recall, async await is a way of guaranteeing that a piece of functionality is schedulable, that it can be put onto some later part of the current compilation thread or execution or act or whatever you want to call it. But basically, whenever we call await on an async function, we're saying, hey, I don't need to do this right now. If there's more important work going on, that can go first. I'll wait. I will be scheduled at the back of the queue, right? You can kind of think of it like a dispatch queue. It's not exactly like one, but you can think of it like one, right? So async await guarantees schedulable, okay? Which means if you don't kick off anything that's actually concurrent, async await looks and runs exactly like synchronous code, okay? So async await is not about concurrency exactly. It's not about things running in parallel. It's about things being able to be scheduled. And then we can happen to schedule things to run in parallel, right? And that's done using tasks, okay? So you use the task to kick off a new sort of, execution thread, right? Now, there is, basically kind of, there are a few specific default things, like places where code can run in Swift. And I'm going to write on the whiteboard here a little bit. But basically, you have your main actor, which you all have seen before, I'm sure, right? And then you have your non-isolated context. So the non-isolated context is basically just a giant bucket where anything that gets dispatched and we say, hey, we want to run this, we don't want to run this on main. We want to run it somewhere else. We want to run on a different thread, right? It'll get sent to the non-isolated context unless you have specifically indicated through some syntactic means that it should run on a different actor context. So by default, anything concurrent that you use async await for gets sent from main actor over to the non-isolated context. In order for that to work, of course, if you're passing any data in, it needs to be at sendable because you're sending it across a line. If you cross a concurrency boundary, it needs to be at sendable. All right, so you call like await, send message, and then you pass it a message, right? Whatever the type of this is needs to be sendable, okay? Otherwise, it won't work. Oop, pardon me. Okay, so default concurrency is non-isolated context. When you kick off a task by calling task dot what is it detached, I think, right? Normally, if you call task from anywhere, it will inherit the concurrency context that it is being called from. For example, here we have this try await task dot sleep. That is inheriting the current concurrency context. Now, the current concurrency context, or also known as concurrency domain, as I put in the comment there in the code, is the reminder concurrency domain. This exists because we have declared an actor, okay? So having an actor type is basically like having a class type. It's a reference type, but the main difference is, oh gosh, that's magnetic. I always forget. Slammed down the eraser a little too hard there. Okay. The actor reminder here, any work that happens inside of functions on reminder that involves stored properties on reminder that just exists within the reminder code. If you do an extension on reminder, any code that happens in there is all going to occur on a new reminder actor context, which can run concurrently with these other concurrency domains. Every concurrency domain can run in parallel to each other. They are their own little swim lanes, their own little dispatch queues that can just keep going, okay? So that's a better, I think, explanation of concurrency than I gave in like the 45 minutes in the concurrency class. Are there questions about this? Cool. Okay. Right. So once you have your concurrency set up and you understand what's happening here, it tends to be pretty simple to use, and Swift will not let you use it wrongly if you are building with Swift 6. It will give you compiler errors that say, hey, you are breaking some concurrency rules, you're trying to send something across a boundary that's not sendable, or you're trying to call a function across a boundary without awaiting it, right? And so because you haven't awaited it, you know, we're going to try and execute it immediately, and that can cause race conditions and stuff, right? So yeah, this is, you know, basically pretty simple to use in Swift 6 if you know what's happening. Otherwise, it can be very, very frustrating. This is why I did request for your final projects that you set the build to Swift 6 so that you got to deal with and understand these compiler errors as you are building your final project, just so that you kind of, you know, understand and learn and grok the concurrency stuff. Because it's kind of a pain when you're first starting out, but once you understand what's going on, it can be pretty nice to have static compile time checks that you are not causing race conditions in your code. Race conditions in code are one of the hardest things to debug at runtime once you have introduced that error. They're very, very difficult to find and understand what's going on. So, you know, having static checks for that is really, really nice, but it's a little complicated and convoluted if you don't understand, and Apple's documentation doesn't explain this super, super well either. So, okay, no questions about concurrency. We will move on to the next one. Good. And that's the break. So we're going to take 10 minutes. I'm going to eat a sandwich, and then we'll continue. Oh gosh, I don't want to play audio. That's not what I wanted. It's so soothing, so relaxing. Please, thank you. Okay.